we're just taking multiple functions, graphing them on the same axis. That's it. You're just putting them in the same Cartesian plane, and then they may or they may not connect with one another, so they might have points of discontinuity. So think of them individually as, in this case, 3 different equations that I'm graphing. And again, if we just kind of, like the red graph, the green graph, the blue graph. Those are 3 different graphs that we're going to put on that same Cartesian plane. And then we're going to only see parts of them because the restrictions here, these guys right here, they tell us which parts of the graph to look at. So they're called piecewise functions because we're made up of many pieces. And it's mathematics, therefore it's wisdom. Thus, piecewise. Deep. Profoundly deep. Colossal. Alright, so let's do this. Let's graph these things. Let's graph the green. No, start with the red. F of x equals -3. Right, Francis? What is it? Y equals -3. How am I graphing? And it's what kind of a line? Well, all lines are straight.
It starts at -5.
Okay, and it's going through -3. So you're saying it's a horizontal line? Is that what you're saying?
Yeah.
This is a horizontal line at -3. So we got this horizontal line at -3, and it's now here's what she was saying. She made a very good observation. She noticed that it's only going to show up. It's only going to show up between -5 and -3. That's how much of the graph I'm going to see. So we go and we hit -5 right there, and then we go out to, where am I going? -3. Oops, went too far. Right there. Going from -5 to -3 on y equals 3. So we get that. Red. Okay, let's see. Pick on somebody else. Now I need somebody to tell me what we're doing with y equal x, the green graph. Mr. Rose. How am I going to graph that? Y equals x. What does it look like, first of all? Like, where would that graph? It starts on 0, exactly. It starts on 0, and then it would go with what slope?
So 1/1.
1/1, very good. So I'm going to do that. So maybe you do this. Maybe you just start on 0, and you're going to go slope of 1/1, and it would look like this. And I know I'm going to go out to 3, but I'm also going to back it up and bring it to -3. So that's how much of the graph that we see for the green function. Is that green? That's green. Actually, there's my 2 pieces so far. Now let's talk about the blue. Alex, what does this guy look like? X minus 3 squared. Yeah, you, Alex. There's 2 Alexes sitting next to each other. That was very dumb of me. That's all right. So Alex. X minus 3 squared. What kind of graph is that? Very good. And what is the HK of that parabola right now? 3, 0. And does it flip over? Does it stretch? No, there's nothing in front of the parentheses. So I'm going to go to 3, 0. And we're going to put our point. There I am, 3, 0. And I'm going to graph this graph with movements. Left 2, left 1, right 1, right 2. Now, because of the telling me I only want to look at everything bigger than 3. I'm not going to even bother considering the left movements at all. We're just going to graph it from the right movements. So from here, I'm going to go right 1, up 1. And then I'm going to go right 2, up 4. So right 2, up 4. And I get that. And then I would connect that. And I get something that looks like so. And let's see if we've now created our piecewise function correctly. Does anyone see one little oops that I need to go back and fix? A minor little thing here. Check on the green graph. There's something that I need to do. Does anyone see it? Tanner? I need an open circle on. I need an open circle on the 3. Look, there's no bar underneath that inequality, so I have to have an open circle on the 3. So there it is. There's my open circle. Everything else is closed. So the question is that a function, yes or no? Will it pass the vertical line test? Got to know, got to yes, got to know. Okay, look at through the red graph. Is it going to pass vertical line test for the red part of the graph? Through the green part of the graph, it's going to pass the vertical line test. Your point of question is right here, isn't it? Am I still going through one point at x equals 3? Yes. So this is a function. It is a piecewise function. It has a broken component. So we have a point of discontinuity that we're going to have to think about. All right, there was some hands that came up. Bobby, there was a hand.
Oh, I figured it out.
Figured it out. Who else had a hand? You're a comedian. All right. Anyone else? Okay. Now, in that process that we did, where we just chunked it, and we just looked at individual graphs, was that difficult to do it that way? No. Okay. So maybe we suggest ourselves that that's the process that we're going to take with the graph. Do it piece by piece. And if you need to, graph the entire thing and then to erase the part you don't need to see. Remember, the part that you do need to see is this component. This tells you how much of the graph you're looking at is this if part. Okay.
Can you do the blue graph?
Yeah, how do we get the blue graph? So we recognize that it's a quadratic, x minus 3 quantity squared. So it is in this form right now. It's in y equal a times x minus h squared plus k form. So the only thing that's really not showing up, even though it's there, is this a because it's a 1. And then this k isn't showing up because it's a 0. Yeah? So why am I looking at half of a parabola? Good question. That's what this is going to do. Normally my parabola would have looked like another point over here, and another point over here, and then I would have connected through those points, right? But that doesn't mean go greater than or equal to 3. That's going less than or equal to 3, and that's not what this is going to be. So I can't go to these sides because the restriction says only bigger than or equal to 3. All right, those are good questions. So domain. Let's get rid of this stuff. Bless you. All right, so let's describe domain. Let's pick on some. I haven't called in a long time. All right, Alex L. I called it you yesterday, didn't I? Yes, I did. That's okay. Tell me the domain of that graph. Okay, I got -5 is where it starts. And then you say infinity. Okay, very good. Remember that this parabola has an arrowhead on the end of it because it says greater than or equal to 3, which means it just keeps on going. And so I would say that I'm going to just keep on trucking right there from -5 to infinity. There's my domain. Okay, let's pick on somebody else for the range. Who should we pick on this time? Nicole. Nicole. What's my range? Squash it on the y-axis. What do I get?
-3.
Yeah, -3. Good.
Infinity.
Good job. -3 to infinity. Squish the graph onto the y-axis, and I get -3 to infinity. Very good. All right, discontinuity. Who's feeling brave? Okay, Austin. Where's my point of discontinuity? Where did I break my graph? At x equals 3. You guys are brilliant. X equals 3. There's my point of discontinuity. Discontinuity. It just breaks one place. Now, not all piecewise functions have broken parts. Some of them connect very well to each other. But this is an example where I have piecewise of a point of discontinuity. Do you have a question for Alia? David?
There's still just
Yeah, I mean, these are kind of my generic, we're going to look at these three conditions, domain, range, and discontinuity, but you're right, some of them won't have this component, so just saying that. There's no break in the graph there. All right, let's try one now, or let's you try one. Maybe you can partner up here. Partner up with your neighbor, and let's see what we get. Got a couple of them we're going to peek at. Okay, a little tricky on these now because of this. The whole if part is what's going to, you got to get this component. So here again, we're looking at our red graph, f of x equals 2. Our green graph, f of x equals 2x minus 2. And our blue graph, f of x equals -x plus 4. 3 different lines with certain areas that I'm looking at. Now, what we're going to do here is we're going to graph them individually, just like we did with the last one. So the first one, horizontal line at 2. And I'm only going to see this graph from -2 to +2 on the x-axis. So maybe you do this. If that tells me the part that I see, maybe you kind of give yourself a window. I'm going to go between there, and that's how much of the graph I'm looking at. And I'm going to do this from 2, y equals 2, so it's a horizontal line from there to there. There's my graph. Okay, there's the red component. I had my boundaries that cut me off. That's as much as I'm going to see. And, yep, it looks like, well, we're going to hold off on the open circle for just a second. Let's wait till the very end before we tag our circles. Okay, the green graph. Now, what does that look like? It's a slope-intercept form, and I'm only going to see this one between 2 and 3. So let's go put our boundary lines at 2 and 3, and that's as far as I can go for this graph. So going from there to there. That's as much of the graph as I'm going to see. It's just between those 2 lines. But maybe it's easier, though, for you if you graph it like a normal slope-intercept, which means start at -2. So start there, -2, and then go up 2 over 1. And then go another up 2 over 1. And then go another up 2 over 1. And there is where I would end. But I got to cut part of this line off. I got to stop it right there. There's the green part of the graph. Get rid of our boundaries. Let's go do the next one. The blue part of my graph, also slope-intercept, but this time I'm going to only see this graph from -2 to -infinity. So we're only going to see one boundary line, and then maybe we say, hey, it's supposed to go that way. Because that's less than -2, less than or equal to -2. So we graph it like our normal one, slope-intercept, Started at 4, go down 1 over 1, down 1 over 1, blah, 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 blah. Or it could have gone up 1, left 1, up 1, left 1. So I'm going to drag it, go up 1, left 1, up 1, left 1, up 1, left 1. And it would look like that. But I'm going to bring this other side of the line. And go right there. So I'm cutting off again the part that I don't need to see. Come on. There's my blue line. So if you did this one right, then that blue line, though, would have an arrowhead on the end of it because it just keeps going to my left. And those other ones, I have some circles I need to think about. So let's see, on the red line, I've got a closed circle on the left, which is -2, and an open circle on the right. But, oh no, yeah. That open circle on the right is also the same thing as the open circle on the green one. You'll notice on the green graph, it's also open. And then, let's see, I got an open circle on the 3 part of the green graph. And then it looks like I have a closed circle on the 2, right, at -2. So how do your graphs look in something like that? How many have it looking like that minus the circles? How many have 2 of those parts correct? All right. But what did you think about that process of kind of drawing this like cutoff line to help you know where my graph is that I need to see? Was that helpful? To look at the x values. This is the boundary. This is where it's going to show up between here and here, or to the left of this, or to the right of this. Just graph it normally, and then take that eraser and erase all the parts you don't need to see. Now there's my, that's a piecewise function, and then we're going to talk about domain and range for this thing. Domain. What do we have? Somebody? -infinity to no Buzz Lightyear on this one. I don't go to infinity and beyond. I gotta have to stop somewhere. 2, I gotta stop at 2 because it's an open circle right there, isn't it? I gotta stop at 2, and then what I need to do? Union it with 2 to 3. Yeah. You get it? 2 and 3 both have. Why do we have to union it? Because we've got this break happening here at 2. There's a discontinuity point right there. So I got to break my domain. It can't be equal to 2.
Oh, because it's not.
Because it's not equal to 2. None of those inequalities show or equal to 2. Right? Yes. If one of them was or equal to 2, I don't need to include that. I could have just gone from -infinity to 3. Yeah. Okay, now squish it onto the y-axis. What do I get? What's my range? Take the green, put it onto the y. The red's already on the y, the right spot. Take the blue, put it onto the y. What are we going to have? 2, 2, 2, 2. No, not to infinity. For y. Squish everything onto the y-axis.
2 to 6.
No, not even 2 to 6. 2 to 4. Look at, right? Take this line here and squish it onto, and I only get that much. And then from 6 on, I'm going to get my line hanging out of the y-axis. Yes, brother.
It's not 2 to 6 because otherwise.
Exactly. It's not 2 to 6 because between 4 and 6 there's no graph. Yep. So I'd say this one goes from 2 to 4. Close it with a parenthesis because I cannot be a 4. Union that with a 6 that has a bracket because I can be equal to a 6. And then go to infinity. That would be the range for that one. And then we have a broken graph, so we have some point of discontinuity. I actually have 2 points of discontinuity. Where are they? X equals -2 is a broken point. And where else am I broken? No. You're also broken at x equals 2. There's a hole right there. It can't be equal to 2, so I have a broken graph. That's a point of discontinuity. Boy, say that 5 times. So I have, oh, great. So I have 2 points of discontinuity. I'm broken at 2 and -2. I got a hole in my graph right there at 2, and then I've got a large gap in my y values at -2. So I have multiple points of discontinuity. That was a little tricky. Huh? Tricky. How about it? Any clarification we need to make on this one?
Yeah, the domain and range.
So the domain and range part of it? Okay, so again, think about domain being, let's take these graphs and let's put them on the x-axis. So if I did that, this red line would, boom, land right there, right? Correct? Okay, now let's take this green graph. Let's see if I can rotate it. Probably not. Can I rotate it? No. All right. But you can see that it goes between 2 and 4. It lands on the x-axis. But, 2 and 3. All right, 2 and 3. So it lands on 2 and 3 like that, right? There it is. Take the blue graph, let's bring it down here, and it goes on forever. So now look at all the x values that are covered by our graph. Between -infinity all the way out to 2, but I got a hole on 2. Because of this little circle right there, right? That would have to fit right there. And then from 2 to 3, I've got some parts of my graph. Does that help?
Yeah.
All right, I got to undo it. Bring everything back to where it was. All right. Okay. Let's do some more. Joy. Let's see how many more do we want to do before we. Oh, we got to do absolute value. Can we go talk about absolute value first? We talk about absolute value. Oh no, the backbone. I might need to be leaving and saving some of these blocks. Should I answer Batman?
Yes.
Batman here. Batman here. Hey. I can hear you. Yep. Okay. Thanks. Bye. Alex. Alright, she didn't think I was Batman. Okay, let's talk about absolute values real quick. These are piecewise functions as well. Hang on, I'm just going to move over here. Where are we going? My goodness. Okay. So how does the absolute value function work? So we've got these 2 components. Remember when we were doing this in chapter 2? So we talked about how there's guts of the absolute value. There's positive guts and the negative guts. Does that ring a bell? All right. So we think about that as well. Here, see it a little bit better. So when we're doing this absolute value, we have one part of the absolute value that has a positive slope, and the other part of the absolute value that has a negative slope. So this is what makes them the same thing as a piecewise function. So here we have absolute value of 5 is equal to a positive 5 in the guts or a negative 5 inside the guts. How do we think about this graphically? So if we have f of x equals to the absolute value of x, that means inside the guts can be positive or negative. And here's how we designate positive or negative. Again, going back to our chapter 2 stuff. If I'm bigger than 0, we're saying we have positive. If I'm less than 0, it means we're having negative. So if I were to split this thing up into the positive slope part of f of x equal x and the negative slope part of f of x equal x, I have two equations that are now slope-intercept form. Y equals x, and y equals negative x. And these two lines would come down and they would meet at our vertex, which in this case, the parent function, would happen at 0, 0. So what do we do when we're doing piecewise? Whatever is inside of the absolute value bars, we're going to write it as that value, whatever that is, one of them positive and one of them negative. The if components will always state greater than zeros and less than zeros. And that is how we turn a piecewise function with two linears that meet at a common point and into an absolute value. So let's try some of these and see what happens here. So here's the generic rule. This is the model we're going to use for all of our absolute value functions. Make one value of the guts positive, another value of the guts negative. The positive part will always be greater than or equal to 0, and the negative part will be less than or equal to 0. And these two will always match. Whatever the guts are will always match. So that was absolute value of x minus 3, for example. Then I'd say f of x equals x minus 3 if x minus 3 greater than or equal to 0. And f of x would equal negative of x minus 3 if x minus 3 is less than 0. And we're going to take a look at one of those right now. This one. F of x equals x minus 2. So we're going to have positive gut of x minus 2 and a negative gut of negative x minus 2. So here's what we do. First, we're going to write them and then we'll graph them. Remember, take what's inside of the bars, make one of them positive and one of them negative. For the one that is positive, this will be where we have to be greater than or equal to 0. For the one that's negative, we're going to be less than 0. And then what goes there, again, whatever is underneath goes right here. That's my setup. So whatever's underneath those guts. And let's see if this works. Let's see if we get two lines that intersect at some common point and create this V-looking shape. We have a little work to do on our if parts over there because I can simplify x minus 2 greater than or equal to 0. I can simplify it to become what? How can I simplify it? X is greater than or equal to 2. And then this one simplifies to what? X is less than 2. All right, so let's see what we get if we graph this piecewise function. Let's pull in that. All right, there we go. So we've got, again, we'll separate our two graphs. We'll talk about the green graph. We'll talk about the blue graph, just like we were doing with the last example. So two different lines. One of them x minus 2, the other one is actually negative x plus 2. If I were to distribute this negative through, this would be negative x plus 2 right there. So, x minus 2, that's a graph that starts at negative 2 and has a slope of 1. And where are we going to see it? Let's put our boundary lines in. It says we're going to see this graph from 2 to infinity. So I'm going to put my cutoff line. I'm going to see my graph from that line to the right for the first part of this function. So let's graph it. F of x equal negative 2. There's my b. Then I go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. I keep doing that. and I get a line that looks like so. And then we cut that off, measure only from 2 to the right. All right, so far so good. There's one side of my V. Now we're going to do the other one, the negative x plus 2. And this one we're going to see to the left of 2. So now we're looking at going this way from that boundary line, where the green graph was going right of that boundary line. So we graph f of x equal negative x plus 2. We start at 2. We have a slope that's going down 1 over 1, down 1 over 1, down 1 over 1. We get to that. Sorry to just stretch it out a little bit here. Okay. Oops. There we go. We get that side. And look at that. Created a V. These both have arrowheads because it says greater than or less than, so they just keep on going. But there's your piecewise function, aka absolute value. Yes?
Will both sides of each side of axis will always be somewhere?
Now, when you say symmetry, you mean the length of the arrows symmetry, or
the center?
so will the center line separate the two?
Will they have each side always be the same?
Yes.
So
No. Yo, okay, I get what you're saying. Okay, good question. So he's saying, like on the green line, if that has a slope of 1, will there ever be a time where the left-hand side has a slope of negative 2? And the answer will be no. They will have opposite slopes. So those are the same. It depends on your if parts, if we restrict somehow the if parts. But if we don't, which is normal for absolute value, we don't restrict them. They just have the same side E component. All right, so that's absolute value. Now we've talked about how in absolute values, what an x minus 2 does is it actually says, let's take our graph and move it to the right 2, is what that is saying. It's up there's my H, that's my H. So my HK in this problem, just like a parabola, would have been 2, 0, and that's where my starting point is, whereas the vertex of an absolute value is the point where the 2 lines meet. So that's where it started, and that's exactly where it started. It's at 2, 0, and then it created the V from that. All right, what questions do you have?
Domain and range.
Oh, yes, domain and range. You tell me. What's the domain of a graph that keeps going forever and ever both ways? All reals. All reals. What's the range of this graph? Look at it. Where's it going from? Squish it onto the y-axis. Y's are going to be greater than or equal to 0 in this case, because it starts at 0 and then it goes up. All right, I think we're going to run out of time, but we only have a few new items to look at. Well, I didn't say we're done. I just said we're going to run out of time. No, we're not. We're going to see if we can get one more in. Just one. In 3 minutes. It'll be record speed. All right. No, we won't. We won't have time. We'll do it tomorrow. So we'll pick up with this tomorrow. Try and get your homework as best as you can.